Hi everyone, my name is Xin Chen. I'm a lecturer in School of Computer Science, University of Nottingham. Today I'm going to give a mini lecture to give a brief introduction of machine learning. Okay, so during this lecture I'm going to cover what is machine learning, the aim of machine learning, and also the general pipeline by giving a data, how can we process the data, and what are the popular methods to build predictive models to predict incoming events. And also I will talk about evaluations. Once you build the model, how do we normally evaluate it? What are the important aspects throughout the pipeline of using these different machine learning methods? Okay. So to start, we want to talk about what is machine learning. Talking about machine learning, we have to mention the word artificial intelligence, AI. So AI has been very popular word in nowadays. Almost every field in talking about AI, try to use AI to help human to reduce their workload and help making decisions intelligently or robustly. Actually, the AI was started in 1950s. In their early systems, AI systems, people need to use conditions or rule-based systems. For example, if certain conditions were met, and then here's the action. You need to do this, 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 and you can design different conditions basically. But you can easily imagine that if a scenario or a case that outside these conditions and never been designed within these conditions, there will be a problem, right? And it's not normally this earlier system. This is not robust enough to handle different cases. Truly intelligence, it cannot be met by those early systems. Then since 1980s, people start to think about, okay, I don't want to design those conditions because it need to be really explicit and also is not working robustly, and I may miss some features, right? And I may miss some conditions. So how about I give a set of data, relatively large data, and I can specify a few important features from experiences. Those features, for example, if we want to explore the patterns or predict certain disease by giving a large population, we can extract some features like age, BMI, height, weight, gender, and family history, and so on, to predict, for example, the risk of getting diabetes and obesity, for example, as well. So all these features were human designed, were extracted. We normally also call it handcrafted features. Okay, by having these features, then we feed into a set of machine learning methods, or one of them could be linear regression. It's just a linear model that predict fitting a line basically to predict new events. And a more advanced one including support vector machine, neural network, and random forest, and all those are nonlinear models. Kernel SVM is nonlinear model, and can handle more complicated problems and handle the feature interactions and to model more complicated problems with these nonlinear models. So that's the classical machine learning pipeline and methods. But then since 2012, actually, a new field within a subfield within machine learning called deep learning, and start to boost. The reason it start to really a lot of people talking about deep learning is in 2012, due to the GPU power, computational power, it boosted a lot, and also there's a technical breakthrough. People can start to train a deeper neural networks. Okay, deep learning is mainly based on artificial neural networks. It's particular modeling techniques. But with classical machine learning, people can only train very shallow networks and with only 2 or 3 layers. And then if we have a deeper layers to handle more complicated cases, it cannot train. The errors cannot backpropagate. So that's the key problem. But since in 2012, there's a group of researchers and can able to train deeper networks with a very small trick we can talk about later in a different lecture. So once you can train deeper and deeper networks, and the network is able to handle larger and larger data, a huge amount of data can be learned from. So once you have a large data, the performance, you can imagine the performance will start to boost. That's why deep learning nowadays is the #1 choice if you have enough data in your problem. And in the field of computer vision and medical imaging, actually deep learning is like 80% of the papers are already using deep learning. But still, machine learning is very classical. Machine learning is also popular choice when you do not have enough data to train your model, and also sometimes even performed better than deep learning. I have to say this. I need to emphasize this: is deep learning is not always the best choice, dependent really on the data itself. Okay, if you don't have enough data, and if you want to have dive a bit more details how to explain your features and have explainable methods, and maybe machine learning classical method is your first option. We'll discuss this a bit more later. So in summary, artificial intelligence is a broad area, and also it covers machine learning. Machine learning is a subset of AI. And deep learning is only a particular method within machine learning. Okay, so here's the relationships on the right-hand side. So next, we want to talk about what is the aim of machine learning, what machine learning can do. Normally, we want to train machines to explore useful features and learn data patterns from data to predict and infer a target event. When feed into features from a new data, we want to predict the target event. So broadly speaking, we can split the machine learning into two methods, and one is supervised learning, where the key aim is to build a predictive model by feeding into both the features and labels. Here features represent, for example, the age, BMI, and height and weight I mentioned to describe the data. And also labels here is the outcome event, which is for example, disease, non-disease. So by feeding both the feature and corresponding labels to some algorithm like linear regression, neural network, and so on, we can build this model, ask the models to feed a particular pattern to this data to learn the correspondences between the label and features. Then when you have a new data, you extract the same sets of features and feed into the model, the trained model, and the model is able to predict the label, therefore the outcome events. Okay, so in terms of the outcome, normally we have two different groups. One is classification, where you have the categorical groups like disease, non-disease, or different disease severities like healthy, mild, and severe. So you can have multiple classes. The next group is regression. In this case, the output event is continuous measures. Okay, so for example, we can use MRI brain image to predict the age of this particular brain. So in this case, the age is continuous measure, so it's called regression. The second group is unsupervised learning. In this case, the key difference between the supervised and unsupervised learning are the unsupervised learning, we do not have any labels. We do not have the outcome events given for the training data. So the key thing is here we want the machine to explore any patterns or relationships within the data. For example, classical unsupervised learning is, for example, k-means, and also nowadays more advanced one, we can also use deep learning like generative modeling to learn the underlying patterns between each other, between the different data points, and to map the high dimensional data into low dimensional latent space to see their relationships between different data points. Okay, so but the key thing is to group the data and to explore their relationships between different data points and try to make some meaningful interpretations to understand the data itself. We call it clustering. Okay, so generally speaking, this is the general structure of what machine learning can do, the aim of machine learning. Okay. So far, I talked about features and outcome events and labels. Hopefully, you were not confused by those different names. So here on this slide, I want to set the scene to make it clear about different names and refer to different things within the context of machine learning. Because machine learning is highly related to probability, statistics, and sometimes people may use different names for different things for the same thing. Basically, they are interchangeable. So hopefully, when you see these words in the future, you're not confused. Um, so because machine learning is based on training, based on modeling on a training data set, and people often talk about observations and instances. So here, observation instance refers to a particular data point within the data set. Okay, for example, an instance could contain the features and the outcome events. It's like wrapped up like a package for individual points within that data set. Okay, and then we talk about features and the predictors and attribute or input variables. All these things, they are in general representing the same thing, like features like color, weight, and height. Okay, they describe the characteristics of that data point, of a particular data point. It could be called predictor and feature, attribute, and input variables. Okay, and then is the outcome event. When we talk about outcome event for training data, we normally call it label. Okay, so it's like could be categorical, could be age, could be different continuous numbers, and it refers to outcome event. And then when we say the outcome event for a unseen data, we normally call it predicted values or predictions for that unseen data. So the outcome events could be referred to labels, could be referred to a prediction from a particular model. Okay. So here comes the general pipeline of a machine learning process. Here it particularly refers to a supervised learning. So we have start with training data. We collect it from, for example, a real-world problem, and then we need to understand the data to extract some features to represent the data, because the original data could be really in the high dimensional space, could be imaging millions of pixels. And we want to represent extract some features to represent the image, either locally or globally, to end up with some features. And then feed these features with certain labels, could be disease, non-disease, into a training algorithm. And then we end up with a model, that trained model that could be applied or deployed when you have a new data. You extract the same sets of feature, and fit into the model, and then you can have some prediction. Okay, then very important thing is we need to also evaluate the performance of this model. Normally, we'll talk about evaluation later, but normally we need to evaluate the model and feedback to say whether I'm happy with the performance with any unseen data. Does it give a very accurate prediction? If not, we can either revisit the features we extracted or choose alternative options for building the model, a different algorithm. For example, if the linear regression doesn't work, probably we can try random forest to see It could be a more complicated relationships between the features. So normally we need to redesign or re-extract the features and select the proper features, and also choose different methods and according to these different sets of features. So this is really a iterative process. We never deliver a machine learning model with simply based on the training model, extract the features and build the model, then here you go, use it. We never do that. It's not that smart enough. But there's automatic machine learning pipelines been developed recently by Google. It's called AutoML, which can do this automatic feature extraction and training and do this evaluation, this automatic process. But still, it's not working robustly and intelligently enough. Okay, so still, we want to, as a human, we want to control this, and we want to interfere with this iteration. To have a good model, we need to know the limitations of the model. There's no perfect model, machine learning model that can handle every situation, can be generalized well. That's the number one lesson, message I want to deliver. Okay, there's no perfect model. So you need to basically explore the limitations of your model through this evaluation. That's even better than keep improving the model. Actually, you know your limitations, you know your usage scenario. Okay, that's pretty important. When you deliver the model to your end users, you need to it would be better to explicitly say, you need to use my model in this scenario. If anything outside this condition, okay, probably I cannot handle it. Okay, it's much better to say that rather than say, oh, here is the model. It's working robustly. You can test it and try by yourself. Okay. So here I want to start to discuss the individual key components within the pipeline. Let's start with the data understanding, representation, the pre-processing. When you're given a data set, what are the first thing you want to do? Okay, how can we build the machine learning model? What are the tips and the things we want to go through? So I would suggest, and basically the first thing, to understand the data, understand the underlying problem itself. Okay, and normally you were given this, for example, the spreadsheet and contains all the features and all the instances, and normally the row representing the instances and or observations, and column representing the features. For example, you can give in a data set and with different features to predict breast cancer. Okay, um, but how do you know which feature to use and which feature to exclude? Normally, you need to. It's very good practice to talk to the clinicians and to understand the problem, because they don't necessarily to clean up the data for you, and a lot of the features are redundant. A lot of the features are crucial to be excluded or included. Okay, normally the clinician will know what features are very, very important from the literature. You need to include that, and some of them they are not sure, but you need to understand it. Here's the example. I can't remember the source the source of that example, but they remember exactly the problem. So they were trying to predict the breast cancer or non-breast cancer by giving a set of features. They were tested the model pretty good in their local data set. They achieve very high prediction accuracy. They are very confident about the model. And then they deliver the model to hospitals to use, different hospitals to use. But none of them, the hospitals, can repeat their experiment, can achieve that accurate prediction. So then they revisit the problem. What was the problem? They find out there is a particular feature called the name of the hospital. Okay, so they discovered in their data set there some of the data, or a big portion of the data, is coming from a hospital called Cancer Institute. So a lot of this data from this Cancer Institute will be cancer patient. So the model smartly pick up the name and saying it's a cancer highly related to these cancer hospitals. of course, you have a very high prediction. When you see the cancer, name of the hospital refers to Cancer Institute, it's very likely this case is cancer, right? But of course, when you deliver the model to a general hospital that do not have the name or as indicator, they cannot basically repeat it. Here, you build a bias model by didn't carefully select the feature. So here's a typical example of you need to carefully understand the problem. You need to know what feature need to be excluded, especially exclusion of certain features is pretty important because we can have a feature selection process later. But if you include some features that potentially will bias the model, have a high correlation with outcome events, but other new data cannot generate that predictor or feature, then you have a trouble of that the model. And the next tip is to visualize the data. And you have multiple features. And then normally what I will do is to visualize the individual features and correlate with the outcome events, generate a box plot. For example, for a classification problem, you have disease, non-disease. You can do a box plot to plot the value range and values of different classes and see. You can already see whether these two value range they can separate from each other, can have a significant contribution to the outcome event prediction. Okay, this is pretty important to visualize the data, understand, and look at outliers. If the data point is really sparse and cover a large range, they are not concentrated on small region, then you need to think about what is the reason. Talk these findings with the clinicians. They may feedback to you. So this is also a very important step to interactive with the clinicians who understand the problem better. Okay. The next one is the feature representation or feature extraction. There might be two situations. Once you given a data set, normally you were given a specific set of features already designed or extracted by the clinician. In this case, you don't have any chance to extract new features. That's fine. You can do a feature selection. But in another situation, for example, you're given a raw image, raw MRI data. So you want to extract some features from the image yourself. You can use radiomics feature extraction packages to extract some characteristics to represent the data itself. In both cases, you want to check or you want to make sure certain features whether they can repetitively extracted or represented. For example, the imaging data could be acquired from different machines, but if you use the certain feature extraction method, can you consistently extract the feature or represent the feature within the same range? Okay, and whether this feature extraction or representation can be repeated. This is also important. This is highly related to the generalizability of your model, machine learning model. Okay, the next thing you want to look at is the feature value. Some of the values will be between 0 and 1, some of them between 0 and 10,000. And even larger. So some of the methods, machine learning methods, may not handle the different value range robustly. So in this case, you need to normalize the feature generally, and also exclude some of the outliers, which potentially will also bias your model. And also you need to look at the problem, whether it's categorical or binary classification, or is a regression problem you're handling continuous values. This is related to how we select the feature, the machine learning model methods. Okay, and the next step is to do some data cleaning. We call it data pre-processing. And it could, in most of the cases, you can face the problem of missing data. It's like maybe sometimes you have 20 or 30% of data is missing due to practical problems, and it's just missing. There's no perfect data in real world cases. And there could be some errors. For example, age of 999, it definitely is an error, right? So you need to exclude these errors. If you have a lot of those errored data, it will potentially have a really bad impact to when you build the model. And when you do this clean and missing data and handle the errors, it's better to build a program to automatically handle this case and to do a check, because potentially you will have a new data set and a new problem to do this. You don't want to do manual checkings, but you need to do some evaluation, see whether this handle all of the cases, and don't create any errors by yourself by this program. Okay, but try to do a generic pipeline or data pre-processing pipeline to handle this error and missing data. Okay, so all this is pre-processing steps, and looking at the data, understand the problem, and do a data cleaning. It actually occupied more than 50% of the time for data scientists when they get new data. Okay, it is sometimes a data scientist is a boring job, because a lot of the time was concentrated on understand the data, clean up the data. So also this is crucial step to build a model later, because all the modeling step is just there's a ready built packages. You can simply use it. So the performance is highly dependent on the understanding of the data and representing the data and cleaning of the data. Okay, so this is, I need to emphasize this. This is more important than doing the modeling itself, to understand the data. Okay, hopefully you get the message. So once you have you have cleaned the data set, you have a data to work with. The next thing is to do modeling. No, unless you have a very good feature set that already been confirmed by clinicians or other experts, and saying these are the features, you definitely need to include it, and you don't need to look further, and there's no more features to include. Then you don't need to do this step on this slide. Otherwise, in the normal process, we need to do a feature selection step and dimensionality reduction to reduce the number of features, to remove the redundant features, to only keep the useful ones, and then go through the modeling process. Why we want to do this? Why this is important? Okay, this is highly related, also related to the performance of the model. So one of the first thing about why we want to do feature selection is try to avoid the problem of curse of dimensionality. Okay, what is curse of dimensionality? Is the number of features is relatively large compared with the number of instances you obtained. So I'll give you a simple example. If I draw this. So imagine with a simple case, we have a 1D feature and feature 1. Okay, now you have only have two data points here, 1 and 2. So now we want to do a classification to classify, yeah, we need to classify it. So I will use a different pattern here. This is a healthy one. This is a diseased one. Okay. Now I want to use this feature F1 to classify them. I can easily classify them. Draw a line here, draw a line here, draw a line here, draw a line here. Okay. That's a very easy job, right? So then the problem is when you have a new data here, here, and these lines are wrong, right? And this line is also wrong. Only this one is correct. But if you only have a limited number of instances, how can you do a good modeling, right? So this curse of dimensionality refers to you have a really sparse number of instances in your feature space. Okay, so this is your feature space, and this is your observations or instances. You only have two in this case. So how can you make a good decision between them? Okay, you need more data points. So this will apply to a high dimensional space. And normally the rule of thumb is you want to have the number of features is less than much less than the fewer than the number of instances. Maybe normally 10 times larger of the instances need to be 10 times larger than the number of features. That's the rule of thumb. But the fewer the features, the better in terms of the modeling. Okay, and once you have fewer features, it also helps with the computational speed when you do the modeling. Okay, so this is the aim why we need to do feature selection and dimensionality reduction. And removing the redundant features will also improve the performance. You don't want to include features that doesn't correlate well with the target. It will potentially create some troubles and create some bias to the model, create some wrong information into the modeling. Okay. So there is two types of feature selection we will talk about. What we call feature selection is we want to select a subset of the original feature set that retain the original feature meanings and values. For example, you have 10 features, you end up with 3 features, which is the original features out of the 10. Okay, there are a few methods like filter-based method, wrapper-based method, and banding methods. There are loads of different methods we can use. But I will not cover the details of those in this lecture. And another option is to do dimensionality reduction. For example, you have 10 features. I want to reduce the 10 features to 3 by some combinations of these 10 features, like method like PCA, principal component analysis, and LDA, and manifold learning can reduce the dimensions from very high dimension to a low dimension. But the difference is now the reduced dimensioned features no longer maintain the original meaning of the original sets. Okay, it's a combination of the original feature, but just in a low dimensional space. Okay, so that's the differences. There are different options. Depends on the application. Sometimes if the original one is just the image and you don't want to have you don't have any meanings, then you can use the dimensionality reduction methods. But if you really want to retain the original meanings, you want to select certain feature selection methods rather than simply reduce the dimensions. Okay, depends on the application. Now, finally comes to the modeling process. Once you done the data cleaning, once you select the good features, and then is the modeling step. In this case, I will talk about the supervised model first. The aim is to build a model that able to predict based on the learn training examples that contain both the features and labels. So there are two types of model, like I mentioned, regression and classification. There are a few popular algorithms I listed here. I don't want to go through details and of the working principles of each of these. I will show you a demo later in a separate video. But generally, they can be separated into linear models, where you just have a linear relationships between the predictions and the features. And also non-linear models, and can able to handle more complicated feature relationships, like kernel support vector machines and the random forest and artificial neural networks. All those are the typical and the very useful ones to use. But here is just a few tips. You need to understand the case, when to use a different method. So whether it's related to whether the problem you're in hand is a categorical classification problem or regression problem, and how complicated the features, and whether the features are independent from each other. If they are independent, probably you can just use a linear regression, linear models to do the estimation. If there is a complicated interactions between the different features, then probably you want to use nonlinear models, and also dependent on the number of data points in your training data set. Okay, so all these practical problems I will cover in a separate demo video. Okay. So as I said, this is probably one of the most easy and straightforward and process. Once you clean up the data and understand the problem, and here is just to apply some of the standard method. By assuming you're not into the technical or reinventing different machine learning methods, that's a different story. Okay, but if you just want to focus more on the application, and here is a lot of the packages we have built-in methods, and in Python, in R, in MATLAB, all these methods are built-in functions you can select and play with. Okay. So for the sake of completeness, I will also mention a little bit on the unsupervised clustering analysis methods or pipeline. So here for the unsupervised clustering, we want to divide the data into groups that each of them have a similar characteristics within each of the group. So normally we need to, in the pipeline, we need to define a similarity measures between each of the data points using their feature representations. Okay, so these different similarity measures, including Euclidean distance, cosine, Manhattan, or Jacquard distance measure, and to measure how similar each of the data point with certain features that are similar to each other. In terms of clustering algorithm, there are different categories. So one of them is centroid model. A well-known one is k-means, and the connectivity models. And you have this hierarchical structure method, and also density model depends on the density of the data points. And distribution models like expectation maximization, EM algorithm is also a popular one. So again, I will not go into details of the technical bit of each of this method. And also this is pretty standard ones for clustering analysis. And also lately, as I mentioned previously, you can also use generative modeling like GAN to learn the mappings between the high dimensional space to low dimensional latent space. In the latent space, we call it manifold as well, to see all these data points, their relationships of these data points in the latent space, and how whether they are sitting close to each other or apart from each other. So we can also do this clustering in the latent space to understand the data itself. Okay. And similar to the supervised one, we also need to do a validation to see whether it makes sense to the clusterings generated by this different method and do a comparison. So that's a general idea of using the cluster analysis for unsupervised learning. So once we successfully build the model, one of the critical steps is to evaluate the performance of the model. Right? You want to test how good your model is. Normally, we use a test set with known ground truths, i.e. the actual class labels. In the case of classification, here I listed a few popular evaluation matrices, including prediction accuracy, precision, recall, sensitivity, specificity, and ROC curve and area under the curve measures. So all these measurements are based on the counts of 4 conditions. They are true positive, false positive, and true negative, and false negative. So a lot of people confused about the measurement of the false negative and false positive. The other two cases are pretty easy to understand. So let's look at these green cases. So I draw this table to make it clear. So the columns representing the predicted value, the rows representing the ground truths class labels. Okay, if you have predicted positive and the actual is also value is also positive, you have true positive. And same thing for the negative. Predicted, if the predicted value is agreed with the actual value, both are negative, then you have true negative. Then for the false negative and false positive, for the false positive is the predicted value is positive, but it's wrong, which means the actual class is negative, but you predict it as a positive. In this case, we call it false positive, which means wrong positive. You always look at the second letter. I normally remember this way. So the second letter representing what you predicted. So if you look at positive as a second letter, it means is you predicted value is a positive, but is wrong. You have a false positive. The actual value is negative. Okay, same thing for the false negative. If you look at second letter, then it is a negative, which means your predicted value is a negative, but is wrong. The actual value is positive. So you have a false negative. Okay, the first letter indicating is correct prediction or wrong prediction. The second letter indicating the predicted case. Okay, hopefully it helps to remember it. Then let's look at individual evaluation matrices to see what they're doing. So the first one is commonly used is called prediction accuracy. Is the number of true positives and true negatives, basically indicating the correctly classified numbers divided by the total number of predictions, the cases you predicted. Okay, basically adding up all four conditions, you get the total number of predicted data points. And can you think of a potential problem with this one? I'll give you an example. Okay, so in case of breast cancer screening, where women take a mammogram, X-ray of the breast, then clinicians looking at X-ray and say whether it's a cancer, potentially cancer or not. So the cancer rate in this case is only less than 5%. So it's less than 5% of the population actually will be truly detected, that will be truly suffer from breast cancer. In this case, you will have a lot of true negatives. If you scan 100 women, 95 of them will be negative. That's a true case. In this case, if I produce a machine learning model saying 100% of the selected case will be negative, I don't need to do anything. I don't need to do any fancy training. I just do say all of the input image will be negative. So in this case, if I calculate the prediction accuracy, true positive will be 0, true negative will be 95, and the total number is 100. I achieve 95% of prediction accuracy, which is pretty impressive, right? But does it actually have any clinical usefulness? It doesn't do any good when you apply this clinically. So the potential problem is you need to check whether your data has a balanced example or have the cases that is balanced in order to use the prediction accuracy to judge. And in other words, 95% of the prediction accuracy is pretty bad in this case, right? You didn't detect any positive case. So you need to be careful. Prediction accuracy is a good measure, but do not only look at the prediction accuracy. You need to understand the problem you have and also use other measures to together to look at the problem. For example, the precision and recall. The precision is particularly looking at the number of false positives. we want to minimize the number of false positives. If you have a large false positive compared with the true positive, and you will have a low precision, which is bad. So the higher the precision, the better. So we want to minimize or reduce the number of false positives. Okay, all this TP, TN represent the actual number of the true positive and true negative and false positive and so on. Okay, this is the number. So we want to reduce the number of the false positives. And similarly for the recall, we want to reduce the number of false negatives. Okay, this precision recall is you need to look at them together. Okay, not individually. So they kind of indicating whether your model is over or underestimate of the prediction. Okay, whether you have a lot of false positives or have a lot of false negatives. Okay, and similarly, we have other measures like sensitivity and specificity. Sensitivity is exactly the same measure as recall, it's just a different name. The specificity is looking at the false positives. And so you have, but in regarding comparing these false positives and comparing with true negatives, okay, it's slightly different from the precision. Okay, so based on sensitivity and specificity, we can generate a curve called receiver operating characteristic curve, short ROC, short for ROC. And this is widely used and comparison metrics and or graph to represent the performance of machine learning model. So on the right is an example of ROC curve, and this blue line is the actual ROC curve. How do we generate this? So for most of the machine learning model, the output is not the directly class number 0 or 1. It's actually some values in between 0 and 1, indicating the likelihood of being negative or positive in the case of classification. So it's also some sort of probability value indicating how likely this case is negative or positive. So in this case, we can apply a threshold on these predicted values. And we can apply the threshold between 0 to 1, like 0.1, 0.2, 0.3, or even more densely sample the threshold, like 0.01, 0.02. And when you apply the threshold, you can then have a binary outcome, negative or positive. Anything above the threshold will be positive, and anything below the threshold value will be negative. So by having this positive and negative, you can count for the true positive and these four fundamental counts and generate the specificity and sensitivity values, which is the horizontal axis and the vertical axis respectively. The horizontal axis is a 1 minus specificity. Okay. So you for each of these, by applying the varying the thresholds, we can have multiple points and multiple counts calculation of the sensitivity and specificity. We apply different threshold. So then we can connect these points together. You end up with this blue curve. So this is representing the overall performance of a machine learning model, and for comparison of different methods. And how do we measure the comparing it? We're not comparing the curve. We're comparing the area under the curve, which is this region here I'm scanning through here. The area under this curve. It will normally also between 0 and 1 is a normalized area under the curve. The higher the better. So like I indicated in this blue arrow here, this curve towards the left top corner is better. And the perfect case is we have one area under the curve. Basically, we have a perfect model. You are correctly classify the test case for every case that you tested. And worst one, it will be close to this random line here. The random line indicating I don't need to build a machine learning model. I just simply a random guess. If you do random guess, will be close to this line, random line, okay, which is the diagonal line of the ROC curve. That's the worst case. Yeah, so, but in clinical practice, when we this is good for writing a paper, or good for comparing different methods, but it doesn't give you indicating of how to use it clinically. What does when you have this ROC curve, how can I use it? What does it mean? What does it mean when we apply this? Normally, how we use it is we normally either fix a point for specificity or sensitivity. It depends on the problem itself. For example, if we want to have a really low number of false positive, in the case of breast screening, we if we say it's pretty terrible, if we say it's not cancer, but we say it's cancer, it will be horrified. People will be scared, and if we have a very high false positive rate, then people will be suffer more likely to suffer from mental problem rather than breast cancer. If you tell them you got breast cancer, but actually they're not. So we want to have a really low false positive rate. And then we can select a point here, say, okay, I want to have only 1% of false positive rate, and which is the specificity, right? And specificity will give you very high. We want to have a very high specificity by minimizing this false positive number. So in this case, we will have a very low value in the horizontal axis because it's a 1 minus specificity, right? And we have a low value here. Then we draw a line up and see what is the corresponding value of the sensitivity, right? In this case, it's also very low. So which means if we want to achieve like only 1% of the specificity, 99% of specificity, and this model wouldn't do any good because in this case it cannot detect any good case, positive cases, and is only successful detected is only less than 10%. It's maybe 5% or so. So it's not very good in this case if we want to use this clinically. But if you look at, for example, I'm not really is more complicated clinical case problem. The best maybe we could live with 30% of 70% of specificity. In this case, we draw a line of 30% here and draw above. In this case, we can do 60% sensitivity, which is relatively good, right? In this case, maybe it's clinically useful. So how to use this ROC curve and clinically meaningful, you need to look at the specific case, your application. Okay, so that's all the key messages I want to deliver for this classification when you evaluate matrices. Okay, hopefully you get the message. Again, for the sake of completeness, we talked about evaluation matrices for classification. Here I also list 3 popular evaluation matrices for regression problem, where you have continuous measures. You want to compare with the predicted value. The first one is mean squared error, which is represented by this equation. Y is the, like I said, Y is the observed value, which is the real value. And y hat is the predicted value. So we take the differences and take a square and sum all the cases together. N is the number of data samples you evaluated, and come up with, take an average. You have the mean squared error. That's where the name comes from. So why we use, normally people use this one is related to the optimization problem. Normally people use the least square to fit points between the 2 points, and so the squared error is easier to calculate in the sense of least square, but it's not necessarily the best measure because it has a squaring effect. What do I mean by that? If you, for example, the larger arrow will have a larger impact to the arrows. Okay, if you have a lot of larger arrows, the the arrows of measurements of the mean square error will be exponentially increased, and we'll have a larger arrow compared with the smaller arrows. So there's a inflating effects of that square by using this square. So this comes to the second measure, and you can do a root mean squared error. You simply took a root, square root of this MSE measure, which is this equation. And one thing to mention that a lot of people confused when they calculate that. Do not calculate this as the average of the square root of the MSE. So the square root need to be outside this mean. Do not do a square root inside this and then calculate the mean. They will end up with different values. Okay. And so this is standard definition of the root mean square error, not mean root squared error. Okay, root mean square error is come with a sequence. You do the square root finally in the final step. Okay, and different from the mean square error, it doesn't, well, it is similar to the mean square error. It's still punished more on the large arrows because you do the square roots later after you sum and things like that. But one advantage is it retains the original unit of the target value. For example, if you do age regression, if you use mean square error, is like age of 4, but actually it's a squared. You cannot interpret the arrows, but if you use root mean square error, it's back to the unit of years. So it has the same unit. And even better measurement, which is not better, it has its own advantages and disadvantages. Another third measure is the mean absolute error. You simply take the differences between the predicted one and observed one and take the mean. So that's it. Compare with the other two measures, and it retains the original unit, like the root mean square, but also it kind of reflects the arrows linearly. It doesn't inflating the larger arrows, so it treats all the arrows in a linear way. Okay, so that's the differences. Depends on your application and measurements. You can choose different measures. Those are the typical ones that use for regression problem for evaluation. Okay. So here comes to the final piece of that jigsaw puzzle. Is we talked about evaluation. We talked about model building, feature selection, and the final very important one is how do we design the experiment? Okay, we know how to evaluate the model, but how can we design experiments? Okay, a few things we need to pay attention here. If you have a small data set, normally for training, validation, testing, we normally divide the data. Imagine you have limited data. You only have 100 data points, okay, for you to develop your machine learning model. Normally, you need to reserve a small set for testing and use a large proportion for training and some of them for validation. So normally this is a typical papers normally use 70% for training and 10% for validation, 20% for testing. Obviously, for the training data, you train your model. And for the validation data is normally for parameter tuning. So a lot of the machine learning model has the different parameters. And the idea is you do not touch the testing. You cannot use the testing data to tune the parameters of your model. That's cheating. Basically, you can't touch it. Basically, you need to put it away. And the testing is not within the loop of the development. Okay, you need to reserve it. Do not touch it at all during the development cycle. Okay. And you use your validation data to say to tune the parameters, and normally it's 10% to check for the problem of overfitting. We'll talk about in a minute, and for parameter tuning. So it's also important to reserve a very small amount of data for validation purpose, and then you have the 20% for testing. This is the general rule when you evaluate the model for experiment design. And also it makes sense and to split the data using k-fold cross-validation. So because normally we have limited data, we want to have to explore the full potential of it. If you only fix the 70% of them for training and 10% for validation, 20% for testing, and you only tested 20% of the data, which is not quite good, and you didn't use the full data. In that case, we can alternate the training, validation, testing group by divide the data into k different groups and using k-1 groups for training, and the validation set will be within this training set. You also reserve a small amount of data for validation purpose within these k-1 groups. Okay, and you use the remaining group for testing, and we alternate. For example, you have 5 groups. You use 1, 2, 3, 4 for training, 5 for testing. Then you can use 1, 2, 3, and 5 for training, 4 for testing, and alternate until all the group were tested. In this case, you can have a testing result for all the data you have in hand. But in the same time, you do not include the testing for in the training case, which is a very good way of evaluating the method. It's also widely used, k-fold cross-validation. Okay. And now, when we talk about machine learning methods, when you compare them, it's hardly to avoid talking about model overfitting. Okay. What is model overfitting? I try to explain this in a simple way by using these two figures here on the right. So we have overfitting, then we have the case of underfitting. For example, for classification problem, you have 2 groups and ask you to do a linear separation of the 2 groups. You can draw a line. And of course, you have some failed cases, which still misclassified cases. Okay, maybe in this case it's too simple to just use a linear model to separate the 2 class. And okay, now I want to improve it. I want to use a nonlinear model. I can fit a better curve in this way. You only have 2 cases, which is either negative or positive, which is wrong. In this case, this is better than this one. Okay, I can also use more complicated machine learning model to have I can achieve 100% classification accuracy with the training data, which I will simply draw a curve like that. Okay, in this case, I achieve 100% in the classification accuracy. But if you test new data, a curve like this will not do any good, will not do a better job than this one. In this case, this is overfitting to the data you have. Okay, one of the potential problem issue that causing the overfitting is the curse of dimensionality that we talked about previously. Another one is you train your model for too long. Okay, so if we look at the training process, which is representing in the second figure here, you start, normally the machine learning model is trained iteratively, and this is the training error. And it will keep reducing, keep reducing. If you train it for very, very long, it will eventually reduce to very low error. But when you apply the model at a certain point, and if you train for long, if you apply the model, it will be like something like this, okay, which is not good. We call it overfitting. How can we test that when we come up with the point of overfitting? We normally use the validation set. It's called test error, but actually when we evaluate this, we use the evaluation set. Like I said, we do not want to touch the testing cases. Okay, leave it alone, and we use the validation set to, at each of the iteration, we also want to test a few cases in the validation sets and to see what is the error with the ground truths. At some point, it will decrease, but at some point, it will start to and go up. The error will get larger. So this is the point that you should stop the training and get the model. This is the best model you can get so far. Okay, do not keep training. This is why this is important. You have validation set to detect this overfitting point. Okay, and also for parameter tuning purpose. Yeah, so that's how important it is. And finally, I want to talk about model generalization. And I mentioned this very briefly when we talked about features. There are a few things you need to make sure to make your model generalizable. One is the feature repeatability and reliability. Like I said, for example, images can be acquired in different machines, and can you always get reliable measure from the images from different machines? And normally, also it would be good if you have an independent test case that cover different situations and from different institutions or different machines that definitely you do not have any knowledge of that data. We call it independent test set, which do not have really any relationships between your the test set and your training set. This is different. This external independent test set is different from this test set. This test set is potentially from the same data distribution as the training because they potentially they are acquired from the same sources. But here it could be covered so many different situations. So that's why it's important to test on independent set in order to conclude whether your model can handle different situations and generalize well. Okay. So that's the very key things, very important key things I want to emphasize as well for the experimental design. Okay. So finally, to summarize, I shared some tips and the general pipeline of the machine learning model, the machine learning process. And here I just want to emphasize the key messages I want you to take home. Firstly, when you get the data, you need to understand the data, understand the underlying problem. If you do a lot of data science problem, you become a field expert in different applications like breast cancer, diabetes. So you're supposed to like that, okay? Because you need to know the clinical problem applications and talking to the clinicians when you develop those methods and looking at the features. And also the process of developing the machine learning methods is an iterative process, including data feature extraction, representation, modeling, and evaluation. And you iterate and keep improving the model. And by choosing different methods, choosing different features. And so there's no one single way from beginning to end. It's an iterative process. And also experimental design is pretty important. You need to look at issues like overfitting and when to stop it and how to design properly. The key thing is do not touch your test data. Okay, and also try to use independent data set if the problem if you have the resources to get an independent test set, do that. Okay, and also in terms of the evaluation, how to interpret the evaluation matrices, talk about precision, which may not be reliable if you only look at the precision accuracy, prediction accuracy alone. And you need to look at other measures and together to understand the problem, okay, the performance. And finally, there's no perfect machine learning model as there's no perfect human. Human made mistakes, and we always learn, and always there's different scenarios that happened in our lives, and we cannot handle. So a very good machine learning model is know their limits, know their usage scenario, rather than have keep better and claim it is a robust model. There's no perfect model. You need to admit that in the first place when you do the machine learning. And I don't think this is due to the limitation of the techniques, and because there's no perfect human, and also machine make mistakes as well. So there's always a condition or situation that haven't been entered But if you can, intelligent model will be telling that I'm not capable of dealing this case. That's called intelligence. That the current machine learning method haven't achieved this level of intelligence. That's what we're aiming for. So you know your limits, like human. I know when I will fail. I don't know the knowledge. It's perfect good to say no at certain cases. I can't do that. It's fine. So same thing for machine learning methods. Okay, and finally is if you want to have a play with certain data, here is a UCI public data sets that public available data sets with different problems, real world problems. Uh, and here's the book. A lot of those content is based on this book, and I recommend this. It's written by Chris Bishop, which is a Microsoft researcher and a professor in University of Edinburgh. And here's the link. Has an educational copy of this book, which is freely available. Have a look. It's a pretty good book. And that's it. Hopefully you have a pretty good overview of the machine learning methods and the pipeline and everything. Thank you for listening.